we'll get started in just a minute. We're a little bit late because of traffic. You know how it is in Seattle. It's really bad recently. So today we're going to do something different. Instead of handing out trivia sheets and pencils, we're actually going to use a Google form to take the trivia answers. I could pretend like it's like a really cool innovation we came up with, but the truth is the traffic was just so bad we couldn't stop to get the trivia supplies. But if this goes well, then maybe we will just adopt it. So there's the QR code. We've also put it on every single one of the question slides in case people come in late or whatever. But yeah, get set up, see that the Google form works, and we'll get started in a minute or two. Get started. I realize now, thanks to Barbara, that the questions on the Google form also give you the questions and the answers. So the point of me putting them up on the screen is kind of null, but I'm going to do it anyways. So we'll just go through 30 seconds a piece. If you miss a question, it's on the Google form, so I think you guys can figure it out. So with that, we'll do our traditional trivia, and we will still grade them in the intermission, and we will do the first talk after the trivia. Here we go. So, what? No, I'd never read them. But what might be easiest for these Google forms in the future?
We could do a Google form that just has 1 through 10 with an empty space and A, B, C, or D. And then nobody would ever have to make more Google forms. And they also wouldn't be able to see the questions and answers ahead of time. No, you like went above and beyond. I'm saying like so that you don't have to do that every month. I could just give her the one that's on that. Maybe somebody tried to plug it in. Oh, okay, so that's great. I'll look for it further, but I'll just hand this to you before I start.
Something somewhere got lost.
Down in front. Down in front.
That's all right. We're fixing it. We're putting up the real slides.
Okay, hopefully the Google form experience went well for you. How was it? It was good. Okay, it didn't tell you the answers after? That's good. That's good. Okay. Cool. Maybe we'll do that in the future. So, tonight, we have a very special astronomy on tap. And I say that a lot, but I always have a reason. And here's the reason tonight. It's because our speakers this evening are Barbara Benda and Sam Charney, who also happen to be your up-and-coming Astronomy on Tap leadership crew. Yeah, you can clap. Stand up, guys. Stand up. Stand up so everybody can see you. Good. You can now address all complaints on Astronomy on Tap to Sam or Barbara, because I'm not listening. Yes, so to elaborate on that, as you guys all know from last month, Sam Garza, who has been the director of our social media and outreach, she has now defended her PhD. And yes, that's fantastic. She's on vacation right now, even better. She'll still be around, but she needs to move on to do bigger and better things and all of that jazz. I am now in the last year of my PhD, and I need to write my dissertation and also apply for jobs and have so many existential crises. And Astronomy on Tap just doesn't fit into the schedule anymore. Sorry. So that is why Barbara and Sam are now taking over for the foreseeable years and 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 years. Yep, and thus is the circle of life. So you get to learn a little bit about them today and what they do and their research, which is all super fascinating, interesting. And our first speaker of the evening will be Barbara Benda, who is your new director of social media and outreach. And she is a PhD student in the University of Washington's physics department, which makes her better than us astronomers, if you ask me. And she's going to be talking about galaxy outflows. So Barbara, you are ready to take it away.
All right. So, as I've been doing some research projects, I've encountered these things, little outflows, and I've become really fond of them. They're really cool, and I'm going to tell you about them today, and I hope that I can share some of my appreciation of them with all y'all here today. So, before we start talking about outflows, we got to go back. So once upon a time, there was a cold molecular cloud. And as it was like hanging out in space, gravity does its thing, and it starts to collapse. And then from that, we get some little clumpy bits, we get some stars. And as they live their little lives, they do some things like explode, perhaps, and push some of their metals and stuff that they made out back into the cloud. And we call that stuff feedback. And why would we even consider this kind of stuff is because if we just take the time that it would take this one molecular cloud to collapse into stars, that time scale is like on the order of 1 million years, but what we observe is that these things like exist for a lot longer than that. So there's not just gravity collapsing these things back down. There is something pushing them back out. But like, what exactly is this feedback stuff is not greatly understood. And then to illustrate my point here, I'm going to show a little simulation. And this one is particularly fun because my friend from undergrad worked a lot on these, and I've heard so many rants about this particular project, so they'll enjoy that I get to talk about it here as well. So we've got 4 boxes here. Can you even see that? I am so sorry. So our first one up here is
You might have to pull the microphone with you.
true. Yeah, we've got just gravity here. It's collapsing our stars. And then in the second box up here, we also add not just gravity, but we're also looking at turbulence. So in our simulation, the gas is also mixing back a little bit. And in this third one here, we also have some, in addition to the gravity turbulence, we also have some effects of magnetic fields. It's doing some extra things. And then in the last one, we're also including these jets, or like really like trying to model like what that like stars actually spewing stuff back out is. So as you can see, this swap one, it's done. It took, what does it see up there? 0.7 million years. But the other, particularly the last one, went along for a lot longer. So I'll go a little again here. So if you can pay attention to that top one, the gravity only, you see it just goes whoop, versus while the other ones are still like cooking.
If you want to see it better, you can tune into the live stream that's on our YouTube.
Yeah, we always live stream these things too, which is why we got our fun little setup here out on that first table, if you ever can't make it. So yeah. So that's all well and great, but that's a simulation. I can't just point a camera at a galaxy and then watch it for millions of years. That is not a very human timescale. So we need some other tools to study this kind of stuff. So if we look at our, now we're looking at a spiral galaxy, or my rendition of a spiral galaxy. Top tier artistry, I'm sure. If we take like one star exploding, doing its little supernova thing, it's gonna shoot some stuff out. One part we call outflows. This is the kind of stuff that escapes the galaxy. But there's also kind of some stuff that falls back into the galaxy, and this is the kind of gas that's full of metals that's gonna end up in some next generation's kind of stars. So it is kind of hard to observe this kind of stuff, especially what's going on inside the disk of the galaxy. But we can look at this stuff going out of the galaxy if it's positioned well compared to how we're looking at it. So, and then from that, we can get some clues as to what these actual feedback processes inside the disk are. But that's just one star. There's a lot going on. To complicate things further, there's also this baryon cycle. You might have seen this figure before. It's my take on the classic Tomlinson Peoples and Work 2017 paper, where we've got not just where there's also, in addition to our spiral galaxy, there's this whole like cycle of gas. Like we've got these massive recycling things, stuff spewing out. We've also got some gravity pulling some stuff in from this infalling gas from galaxies around, or from all the intergalactic medium around it as well. Yeah, so it's tricky. So how exactly do we see these things? Sometimes it's really easy. So I've got this one fun example. This is Messier 82, and this is a pretty local galaxy. And this particular image is a stack of multiple different things. There's optical and UV in this like this part here. And then you see these giant things going up and down. That is, I think the red one is some infrared stuff from Spitzer, and the purple one is X-rays taken by Chandra. So it's you take multiple observatories and smush them all together, and you get like some extra information. So like when you do this stack, we can really see that it's active. It is doing a lot of things. So this particular one is it's super starbursty. It is forming a lot of stars. It's also spitting a lot of stuff back out. But sometimes it's not always that easy. See, like, especially if you got this kind of blobby looking guy, it doesn't really look like much, does it? So we need some extra tools. How do we do that? With our spectra. You can look at particular emission lines to get some signatures of gases moving at different speeds. So let's take a more in-depth dive on that. So first we need a spectrum of our galaxy. So we've got one little guy far, far away from us, and we've got our telescope here down on Earth. Our galaxy is emitting light in all sorts of directions, but this particular part of the spectrum is going straight into our telescope. And that is going to collect some of it and then turn that. And inside our telescope, we've got a spectrograph. It's basically like a little prism that's going to split our light. So instead of an image, we get a rainbow, a beautiful rainbow. So yeah, and all these little lines that go up and down, those are emission lines. Those are the things that we want to look at. So if I zoom in on this really big one up here, that one's my favorite one, mostly because it is the brightest one, so it's easy to see. This is the H alpha line. It is with its little companions, the nitrogen 2 doublet. So where do these things come from? So if I've got, so hydrogen alpha is the hydrogen atom. And if I go, it's from if you kick off an electron off this hydrogen atom, and it comes back down to another lower state because our energy levels from quantum mechanics are quantized. If it drops down one energy level from N3, oh gods, it's back. If it drops down, if it goes up to the third energy level and then jumps back down to the second one, it's going to emit a specific, it needs a specific piece of energy to do that, and that corresponds to a specific frequency or wavelength that is also scaled by our Planck constant over there. So we can see that. And this particular one corresponds to wavelengths of 6,562 angstroms. And you might see it doesn't exactly line up here. This particular one is a little bit, a little off by like 20 angstroms, but that's because it's only that angstrom wavelength in the rest frame. So, and this galaxy is a little bit further out, so it's got pushed a little bit further down into the redder part of our spectrum. So that's cool, but like if we have something like this, where is our outflow? Is there anything? So how are we looking for these things? So like I said, in our lab environment or just gas emitting light, we're gonna get a Gaussian. So if you've seen like a normal distribution, that kind of a shape. And then the width of this Gaussian is going to depend on the spread of velocities that you've got. So if I've got gas that doesn't have a really big spread of velocity, it's going to be a lot narrower versus one that has a larger distribution of velocities. It's going to be a lot wider. And then the height of these things depends on the amount of flux that you are measuring. So, or you can think of it like the count of how many photons that your telescope is catching. So that's cool. What if you see something weird like that? It's not a nice Gaussian, right? But I can do this fun thing of I can decompose it into two Gaussians to turn our little red one into a sum of a skinny one, skinny tall one, and a fat broad one, and a short one. And that is the fun thing. That is a signature of an outflow. So nice. What do we do with that? So we're going to jump a little bit here to some theory of galaxy assembly. So I was looking at spiral galaxies. So how do these things end up in our universe? So this one particular, the leading theory that we have right now is that these things have two components, a central bulge and a disk. So you can think back to that molecular cloud that I started out with. We've got this giant thing, some of it's collapsing. We get some stars. My rendition is a little dim about that. And then as those stars live, die, explode, it's going to kick off some turbulence. We might start to see some spinning. And as that keeps going on and on and on, those stars in the center, they age out. So I'm calling them, that's why I changed the color here to red. So now these guys are older, and that then in turn kicks off some star formation in our disk. So now we've got an older set of stars in the central part, and then some younger stars in our nice spiral arms. But like, that's cool, but what if we've got something that's like opposite? Where we've got young stars in the central part, but an old spiral. How does that happen? So this is a particular sample that I've been poking around with lately. We call them break birds. What does that stand for? Where we've got a break bulge, so that denotes star formation in the center, and then a red disk. So break, BRD. Yeah, it is an awesome acronym. No. So how do we find these things? So we took a look in the Sloan Digital Sky Survey, which is this giant atlas of so many galaxies. And we're specifically looking, so yeah, what is this break thing? If you look in the 4,000 angstrom range on your spectrum, a lower number here correlates with a higher star formation rate. So that's like one indicator that you can use to classify your galaxy as star forming. So that's the one that, there's many, but this is a particular one that the Sloan Digital Sky Survey has, so that's what we used. And then you can also select, you can decompose a single galaxy, like those on the left here, we've got some postage stamps of some of the galaxies that I've been looking at. So they've got that little bulge in the center and then the disk part, and then you can decompose those two pieces and then look, say, I want my center part to be star forming, so I'm selecting this 4,000 angstrom break in the center, but also I can select for the color of the disk to be more red. This is what my x-axis here is. So where that red color corresponds with some older stars in our disk. So in green is our little sample of about 120 galaxies that we call our little break birds. And then we plot that on top of like our parent sample of this particular one is broken down into like some star forming and quiescent galaxies, where the quiescent ones are the ones on top in red, and the blue ones are the star forming ones. They kind of make sense for where these, there's like really 4 quadrants here on this graph, where we've got our funky little guys, blue bulges, red disks, red bulges, so old stuff, blue bulges, blue disk, and then our red, blue disk, red bulge. I got confused there. Yeah. So our little sample there. So what are some properties that we know about these guys? Because this original paper was from 2020. We've done some stuff about them, right? So, wow, I made a typo here. Short H1 depletion times. It's not a neural hydrogen. It's a big brain. It's a neutral hydrogen. It's just our hydrogen atom with a not excited electron with it. Yeah, in a classic astronomer fashion, I finished this talk like an hour before, so I did not practice or read through it beforehand. So yeah, so this particular neutral hydrogen depletion times that are short might be some sort of suggestion that they're quenching or like stopping star formation in some way or another. But they have like pretty high star formation rates, which are consistent with actively star forming galaxies. So maybe they have some of them do have, like if you look at the spatial distribution, they're a little bit asymmetric. And then some of them do also have some pretty large metallicity distributions. So maybe they've got some hints of external accretion or in some dynamical disturbances. And then there's been some simulation studies. We're looking for analogs of these guys in simulations. And they see that sometimes the circumgalactic medium, which is, if you think back to that fountain plot that I showed on like the 3rd slide, is the kind of like the surrounding gas from the halo around our whole galaxy. Sam Garza from last week did talk a lot about that one, that particular gas. And yeah. But there's also a lot that we don't know about them. So these are some questions that we've got. So the big one is like, why are they doing their inverted star formation thing? I would love to know. Or maybe they're being like ram pressure stripped. So like if they're going through some sort of like big flow, and then like the bulk motion of the fluid, or which could be on like the filamentary scales, is like stripping gas off of them, so they just don't have any left. Are they quenching? Are they being part of a merger or something at any point in their history? Or are we really looking at, is this really a descriptive enough classification system, or do we really have some like little subcategories? So what am I going to do with them? I'm going to look for some outflows. So we said that we selected them from the Sloan Digital Sky Survey, so we do have Sloan spectra from them. But the Sloan spectrograph has a medium-ish low resolution. Do I remember that number? I think it's like 7,000. So I need something a little bit beefier than that. But that's where the Apache Point Observatory comes in. This is in Sunspot, New Mexico. We, has a nice, like a 25% share in it, so we got a lot of time. So we do get to observe on this thing quite often. And I love using telescopes, so this is awesome. So which one do I really use? I use the 3.5 meter, which is this guy, this big one in the front. It's they're all like opened towards the camera here, which I think is a really cute picture. They're all saying hello. I got to visit this observatory last year, so these are some of the pictures that I have from that. So yeah, this is another look at that 3.5 meter telescope. And then inside of it, we've got our giant mirror here. Like 3.5 meters is huge. Like if you look closely, see this little person over here? I know I'm wearing black, but that's me, but yeah. And I'm not short, I'm like 6 feet, so like it's huge. Just to put that into perspective. I also took the what I would consider an ultimate mirror selfie in the telescope mirror. So like you will never find a cooler mirror selfie than that. So now if I look at it with the domes open, this is our giant thing that's like, it's heavy, it's huge. It's on this blue thing. That's like the arm that regulates how it's spinning. And as right now it's pointed up, the mirrors are open, and then to the side here, you might see this big giant black tube. That is the instrument that I use. What does it do? This is ARCIS. It is the Astrophysical Research Consortium shell spectrograph. It's a really high resolution thing. It can go up to 30,000. So I should probably tell you what this resolution thing really means. So if I look at a wavelength and like, what is the, it's really measuring like what is the smallest like difference between wavelengths that this thing can resolve. So that is a really small difference that it can do. So that's great. This thing is permanently mounted to the side, to the NA1 port on the telescope, like on that one side. The other side, you can switch out some different instruments, but this guy has been on the telescope since it was first opened back in '94. Yes. So how do we observe on this thing? You might think that we've got, I don't have a picture of the control room there, but I do have one from the Rubin Observatory. You might think on site there's a little room to the side where we've got tons and tons of monitors that tell us literally everything you can want to know, from the weather to like what is the what's our seeing, what is the telescope doing, what are we going to observe next, some communications with like your other observers. Like if you manage to go out to the observatory, then yeah. But most of the time, I'm just in my bedroom with my 2 computers, where I connect remotely. It's a lot of fun. Particularly with this one, is the way that the observing software is set up is that it has these really like horrifyingly sounding beeps every time it like does anything, which my roommates don't appreciate. But it's really great because if I do happen to start like falling asleep, like, oh, bam, beep, like our exposure is taken, I will not be falling asleep any time during this this observing run. So that is super useful. So once we are observing, what does our data look like? It looks like this. I don't know about y'all, but the first time I saw this, I was like, what the hell am I looking at? This is not the most interesting thing ever. Like, if you think back to that spectrum I showed y'all earlier, where's that one line with like my 1 pixel of that one line that tells me what the flux is? Like, no, we get this 2D piece of garbage that we need to turn into something useful. So what's like particularly cool about this particular instrument is that it's an shell spectrograph, which is a completely different type. Normally you just have like one slit and it just like disperses the light into one rainbow. This particular one does it in like little bursts, like little batches. So you've got like going all the way down here, you've got little segments of the whole entire spectrum, which the shell part means ladder in French. So you can kind of see that like resemblance here. So yeah, but yeah, after looking at these things for an ungodly number of hours, this one is pretty, like, you can start to like recognize some sort of features, like these little guys over here where we see this one bright bit with like the two things next to it. That's going to be our H alpha and 2 doublet. And then you might see another one over here. Is that another emission line? No, it's the same thing. This as it splits the wavelengths, it doesn't go like doesn't end at one and the next ladder starts at the same exact point. They overlap a little bit, so which is kind of useful when you do your reduction so that you don't miss anything. So how do we? Oh God, I'm a pro. So how do we go from this stuff to our useful spectrum? You do some magic, and then you get something like this. It still doesn't look like much, but it's way better. So you can start to see some features here. Like here's our H alpha line, which is why I've been particularly fond of it. It's nice and easy to see. Yeah, there's not much else here. We've got a lot of noise on both the really bright, the blue end, and then the red end where our longer wavelengths are, which kind of corresponds to like what we see here. There's not much going on up here, and then kind of like loose stuff down here as well. So that's just going to be noise dominated. But if I take this guy, also like this particular step going from this to this took me an ungodly amount of time to like learn. So it's tricky. But we can zoom in on these things, and then like this is a much smaller wavelength range where we kind of zoom in on that H alpha and then 2 doublet. And then now we can really start to see some fun shapes. Like none of these look super Gaussian. Like this guy's spiky. Like these guys have like chunks taken out of them. Like this particular one is like really like sloping this way. And you got the opposite going in the other one. So that's all exciting. So yeah. And then with this, with our data here, if I compare it to what we had from the Sloan spectra, which I plot here in red or in orange, you can see we can really start to see these kind of shapes now. We can really do this decomposition thing where I can describe our emission line as a sum of 2 Gaussians that you kind of couldn't really do with the lower resolution stuff. And then when I do that kind of stuff, I can also like start to calculate like what kind of velocities these two parts are moving at. So our narrower part, which I tend to denote as the galaxy interstellar medium part, that's the stuff that's like mostly in our spiral here. Those things tend to have a range of like 50 to 100 kilometers per second versus our outflows. They're a lot faster. They're a bit wider. So we've got like 100 to 200 kilometers per second stuff. So like there is a difference. They're real, I swear. So if you were like expecting some like nice conclusion, well, this is an ongoing project, so I don't got that. So you gotta keep an eye out. It's coming soon to an archive near you. But what do we got so far? What do I want to do with these things next? So I've got the velocities that I was talking about. Those are really just for like the particularly the H alpha emission line. So like, is it different for are those kinematic different for different emission lines? Because that does kind of they may trace different phases of gas. Do we have different metallicities in our outflow parts versus our galaxy portion to the galaxy contribution to our emission? We can also look at the mass of the gas being ejected and compare that to like the star formation rate / the star formation rate surface density. See if there's any relation there. We really want to look for some sort of scaling relation, or see if that like compares to or how that compares to like some that have been found before to other surveys. And what I also want to do is look for outflow signatures in different wavelength regimes. So instead of just looking at stuff in the optical slash like slight infrared region that we've got for our ARSIS data, I would really like to look at the ultraviolet regime with the Hubble Space Telescope. I did write a proposal for that. It is, I'm pretty sure, being reviewed sometime this summer. So I really hope that the time allocation committee is generous, because this will be so much fun. Why is that particularly cool? Because if you think back to that M82 picture that I showed you earlier, like those different wavelengths are tracing different kinds of gas. So like, is the stuff that's in the visible part of the spectrum, is that moving the same way as the stuff in the ultraviolet? Because those will have some, those trace ions that need a lot more, that have higher excitation energies. So yeah, hopefully that'll work out. And as I was reading through some papers and stuff to talk about today, I did come across one thing that I am actually like really should look into. I don't have any plots on it, but I drew a little what I would like to see from it here. So if I look at the velocity of our outflow, I can also plot it against the star formation rate surface density. So like if I look at my surface area of the star, of my galaxy, and then like look at which parts have the higher star formation rate. So you can trace different kinds of feedback models. So there's particularly two here that I'm going to highlight, is where we've got energy-driven outflows or momentum-driven outflows. So these two are, they kind of trace different processes. So the energy one's going to be, is mostly driven by some supernova. So like as our stars explode, they push some of the gas out, right? So that apparently has a pretty low slope, pretty flat. And then there's also momentum-driven ones. This is mostly just like from radiation off of young stars. So that one apparently has a much higher slope. So I would really like to see, I haven't done it yet, but I will, to plot where my galaxies lie on this. I think that might be fun to see. So yeah, well, there's a lot cooking, but not a lot of results. And as I would also like to say, that's the end of my talk, but it's June, it's Pride Month, so I just want to highlight that space is for everyone. This is the particular, I really like this particular flag because it's made out of all NASA images, which was at one point like the most shared image on Blue Sky. So yeah. And I would also like to highlight, we've got the astronomy, the UW Astronomy Department is going to be really doing a little celebration thing about the Rubin Observatory, which you might have seen some of the questions about. It's going to be releasing some of the first images that this whole thing took. So there's going to be a little celebration for that on June 26th in Kane Hall on the UW campus. So if you're around, it's a free lecture. It'll be a tons of fun, and some, I'm sure, gorgeous pictures. I haven't seen them, but I would love to. So yeah, I have a little QR code here, but you can just Google the Rubin First Look as well. You'll find it. Yeah, they're not going to be stingy about letting people come in. So yeah, so I'm going to leave up my conclusion slides and I guess take some questions. Yeah, what's up?
Do outflows have the equivalent of escape velocity such that like light rail
Oh, so like instead of like
Can you repeat the question?
yeah, so if outflows like are dependent on like material, like do heavier elements tend to stay more inside the galaxy versus are just the lighter elements going out? Yeah, so the elements will leave the galaxy if like if the circumgalactic medium, which is the kind of gas that surrounds galaxies, does have observation elements of heavier elements, even up to like you can find carbon, oxygen, or somehow iron too, as well. So yes, heavy elements do in fact leave the galaxy as well. Yeah, what's up?
Looks like you've got about 15 bits of precision on your spectrometer. That should allow you to get very precise resolution metallicity of these various gas bodies. How far along have you gotten in actually doing that?
Not much. But yeah, I'm looking forward to delving into that kind of analysis.
You should be able to get very good precision.
Exactly, I'm really excited for that. Any other questions? Going once? Going... Oh yeah, what's up? What drives the velocity of these outflowing gas? I guess it is highly dependent on like what kind of process is driving it. So is it an explosion? Is it from a supernova? Is it some young stars that are super active, super bright? So yeah, so like that plot I was showing out, the drawn one. So that should help to distinguish some types of outflow theories. Yeah, in the back there.
Yeah, with what you showed, we were looking at the spectrum. You showed two different velocity distributions, two different Gaussians superimposed on each other. Can you say something more about why that's a good indication of an outflow?
Yeah, it's because you've got these two different shapes. That's a good indicator that you've got like two different gas distributions. So like some of it's moving at like with higher velocities, higher scatter. Some of it's just like hanging out there in one spot. So that's why you can tell that you do in fact have two different things. All right, that's it. Thank you all.
Keep clapping, I'm not ready yet. Still not ready. Yeah. Thank you. That's very generous of you.
So at this point, we will do the trivia answers, and then I will announce the winners, which I wrote down on my phone. And then we will have a 10-minute intermission, and we'll come back with our final speaker of the evening. So without further ado, trivia answers. Okay. The Sagittarius dwarf spheroidal galaxy is currently merging with the Milky Way. I didn't even know that. Hubble's tuning fork classification, a galaxy with a central bar and tightly wound spiral arms is designated as SB, or bar spiral. The two galaxies that dominate our local group is the Milky Way and Andromeda. Spiral galaxies have spiral arms of stars and gas. I mean, come on, right? Okay, sorry, just... what process turns gas in a galaxy into new stars? Star formation. Near-field cosmology studies galaxies and their histories. The Rubin Observatory will repeatedly image large areas of the sky to et cetera, et cetera, et cetera. Stellar streams are trails of stars left behind by disrupted star clusters or dwarf galaxies. Studying stellar streams helps us to map the Milky Way's dark matter distribution. And finally, the galactic halo is the most common place for stellar streams to be found. So, in terms of winners, we have 2 people / groups that got all of the questions right, which is pretty impressive. And we have 2 groups that got only 1 wrong. So, starting with the 2 runners-up, but everybody gets the same choice of prize, so... the first one is Snoopy. Here's that. Nice, well done. The second one is Lewis and Dad. Nice. I think I know who Dad is. And then the first group that got all of the questions right is Inconspicuous number 1. Nice. That's not very Hang on a minute. Are you an astronomy undergraduate student? Oh, you're a graduated astronomy undergraduate student. Well, excuse me. I still think that means you're overqualified for the trivia. But I will let this be the trial of the people. He's right there. Okay, and then finally, the second person who got all the questions right is Grapesicle. Who's that? Oh, nice, well done. You are not an astronomy undergraduate student. That's good. Okay, well done. Then you definitely won. So with that, we're going to go on a 10-minute intermission. If you won trivia, get the prize after the second talk, and we'll be back, with the second talk in 10 minutes. Oh, there's Cycle Docs if you're hungry. And also go get more beer or cider or non-alcoholic beverages from Bickerson's. Thank you. Okay, welcome back. Some of us never left. Hello. Oh, wait. Just hang out for a sec. Okay, it's time for our second talk of the evening. Our second speaker of the evening is my new Astronomy on Tap co-host and successor, Sam Charney. They're buttering you up, and I don't blame them. So Sam and I will be co-hosting through August, and then in September he will take over as full-fledged Astronomy on Tap leader that he is. But for his talk today, Sam is a graduate student in the UW Astronomy department, and he is going to be telling us about one of the first research projects he did at UW, is that right? Called, you know what, I'll let you read it, but it's about stellar streams. Okay, so with that, Sam, are you ready? So actually, while he's doing this, I just have to point out the reason why he's doing tech support is because he's the first Astronomy on Tap host that actually knows how to run the live stream. But he's probably going to be a better host than I ever was. Thank you.
All right. All right. Probably just gonna hold this. I like walking around. So, hello everyone. My name is Sam Charney. I am a first-year astronomy PhD student at the University of Washington. So I am but a babe in the stream of life as of right now. And as a first year, I'm currently doing a series of rotation projects in that I'm rotating through a couple different labs and deciding what professor I want to work with. So this was one of the projects that I did in one of my quarters. This was with Professor Nora Shipp, who is awesome, and she works on stellar streams. So this talk is called, because I don't do anything without giving it a funny title. So this talk is called I Have No Mouth and I Must Stream, and its real title is Teaching Computers to Find Stellar Streams. There is a screenshot from the I Have No Mouth and I Must Scream video game here. You can't see it because it's very dark, but I promise it's there. So,
Did you turn it on?
I did. Oh, there we go. All right. So, the first thing that I need to talk about is that stellar streams is a branch of near-field cosmology. And near-field cosmology is made up of two parts, near-field and cosmology. And we'll need to talk about what both of those things are for you to get where I'm going with this. So, near-field, believe it or not, means... I guess I have to be pointing at it. Okay. It means things that are close to us, believe it or not. Near field is, it's near, we're the field and it's near the field, which is us. And it's things that are close to us. And I'll talk about exactly how close in a moment. And cosmology is the origins and evolution of the universe. So you might ask, how do you get things about the universe from things that are nearby? We'll get there. So, is this near field cosmology? This is near us. Can you find out about the universe? No, this is too near. We're too close. Let's zoom out a little bit. Okay, this is our galaxy. This is an artist's interpretation of our galaxy, because we can't actually see what it looks like from the inside. It's like how if you were like inside of like a dog, you couldn't see the outside of it. For example. So we're around here in the Milky Way. And this is also, we're getting there. We're very close. But this is also still a little bit too close in for us to actually be able to do any meaningful astronomy. As you saw from the trivia answers, you mostly find stellar streams in the halo of a galaxy, which if you're not familiar, a halo extends very far out in the outskirts of a galaxy. The halo starts on the edge here, and it goes like all the way out there. The halos of galaxies are gigantic, and we need to look at the halo. So we'll zoom out even more to the local group of galaxies. There's a lot of text on this, and I'm sure you can't see any of it, and that's totally fine. So the Milky Way is here. That's us. And Andromeda is here. Those are the two main galaxies in our local group, and they're what sort of dominates the gravitational landscape of our environment. A couple other, there's like the Triangulum Galaxy, and there's like Wolf-Lundmark Malotma, no one really cares about those. mostly Andromeda Milky Way. But you can see the main reason I put this up here is because a lot of people, when they think about like our galaxy or the local universe, they think it's just kind of galaxies floating by themselves in space. There's actually a lot more stuff going on out here than just the big galaxies. So you have the two big galaxies, and all of these little dots and little text lines that you can't see are dwarf galaxies. These dwarf galaxies are sort of small bundles of stars, very small relative to the big galaxies, but still, you know, pretty big. But these have such a very big impact on the environment, even though they are fairly small. There's a lot of them. And this is a very important thing to get into your head, that these environments are dominated by mostly these small galaxies and these dwarf galaxies. I also want to point out that, shout out to my parents, Leo and Carina, which are two of the dwarf galaxies that are near the Milky Way, which is a complete coincidence, and also the only two near us that have like normal person names. You know, if you want parents named like Pisces and Groose. Yeah, Groose, for sure. But anyway, I think it's funny that like the two of the interesting dwarf galaxies just happen to be the names of my parents.
And yet they named you Sam.
And they named me Sam, which is not, you know, anything in space. But I'll make it happen. I'll make it happen. So anyway, shout out to them. And this is the local group. This is the part that I'm interested in. There's also the Linear K supercluster. I do think this is cool. The local group is now here, and there's like all sorts of cool big stuff out here that I'm not going to talk about, but it is cool if you want to find out more about large-scale structure. Okay, so what actually is a stellar stream? A stellar stream is a long, thin association of stars. We're very purposefully vague with this definition because a lot of things can be potentially a stream. And it is an association of stars that used to be either a globular cluster or a dwarf galaxy. These are also fairly different, and so streams can also be very different. As these things that are roughly spheroidal in shape fall into their host galaxy, like... What? Can you give me the other one, actually?
Oh, now you want the other clicker.
You know, this one has some features that I wanted, like a timer.
Here's the other clicker. Where'd you put it?
Oh, it's in the bag.
How about you talk?
All right, I'll just keep talking.
I'll do this.
So as a smaller dwarf galaxy, like say Leo or Carina, falls into the Milky Way, the immense gravitational potential of the Milky Way will disrupt the dwarf galaxy, and as it falls in, it'll get torn apart into a sort of long structure instead of its normal spheroidal self. Because as it's sort of falling, the gravity on it is unbalanced. So there's more gravity pulling on the front than on the back, and so stars in the front get pulled harder than stars in the back. Thank you, Megan. Megan will soon not have to worry about any of this, and I'm sure she's very happy about it.
Extremely.
And they also, as I said, they range very significantly in size because they can come from either globular clusters or dwarf galaxies. This is an artist rendition of what some streams might look like. You really can't see them very well because it's bright outside, but they're basically these long strips of stars in the sky. So stellar streams, this is what their kind of size in the sky. As I said, they can be very different. So you have the very small Ophiuchus stream here. This is the whole sky. So this is 360 degrees of sky in a 2D projection. This is the Milky Way. You have Ophiuchus, which is a very small stream, and then you have the Orphan Chenab stream, which goes like all the way up. And there's some even bigger ones. There's the Sagittarius stream that goes like all the way up and across the sky. So it's a very different range of sizes. Because they come from both globular clusters and dwarf galaxies. They also sometimes still have a somewhat spherical shape inside of them. So this is what's called the progenitor, which seems to have gotten a little messed up in transit. It used to be on one line. So the progenitor is this sort of still roughly spherical shape in the top left of the stream that it used to just be a sphere, and it got stretched out into a stream. This one is what they think the Sagittarius stream might look like as it's sort of looping around the galaxy. And sometimes when you're looking at streams in the sky, you can actually see these progenitors still. So based on different sizes, of streams. They come from globular clusters and dwarf galaxies, both of which are roughly spherical associations of stars out in space. So you might say, Sam, that sounds very similar. Surely if you look at them, you'll be able to tell the difference. So which of these do you think is a dwarf galaxy? Which one do you think is a globular cluster? Any guesses? I'm hearing, I think I'm hearing the right answer. Yes, this one is the globular cluster, and this one is a dwarf galaxy. The only difference really is just their size. Globular clusters are much smaller than dwarf galaxies in size. The largest globular cluster is like 100 light years in size. That's, it takes light 100 years to get from one size to the other. And the largest dwarf galaxy is like, even this dwarf galaxy is like 3 kiloparsecs in size, which is like 100,000 light years in size. So dwarf galaxies can be much, much larger than globular clusters. In fact, this dwarf galaxy, which is Fornax, actually has 6 globular clusters inside of it because it is so much larger. This is 4 of them. You can see they look like this. These are globular clusters. So since both of these have spherical shapes and can fall into galaxies, you can get streams from either of them. And these streams also end up with very different sizes. Their globular cluster streams might only be like, fairly short. There's some streams that only have like 100 or so stars in them. There are also some streams that have hundreds of millions of stars in them because they're from large dwarf galaxies. So there's this very wide range of stellar streams. I'm only telling you this just because I want you to know how hard it is to actually find these things, because they're so different, and some of them are really, really faint. You also can get streams in places that are not the Milky Way. This is NGC 5907 that, I promise, has a very large stream looping around it, like this. If you want to Google NGC 5907, you'll see this picture, and it is very cool, because there's a very big stream that is looping around it that is caused by a dwarf galaxy falling in, just like it is caused by that for us. So that's just cool. It happens all over the place. Maybe it wasn't a problem with that clicker. This is a map of every stellar stream that we know of around the Milky Way. We currently know of 141, which is pretty good. We can find out some good things from them. You can see this big red one in the middle. That's Sagittarius. We'll come back to Sagittarius. Sagittarius is a big problem. It makes certain things difficult because it is very bright and very large and contaminates things. Sagittarius has over 100 million stars inside of it, and it takes up the entire sky, basically. So this is all of the stellar streams we know of, which is cool. There's also, you can see the LMC and SMC in here, which are 2 large dwarf galaxies that are around the Milky Way that'll make their way in eventually. Why does any of this matter? So this is the cosmology part. We talked about near field a lot, a little too much maybe. This is the cosmology part. This is why it matters. This is how we can tell things about the universe from stellar streams. So you have a stellar stream. This is GD1. I'm actually not moving that much, so I'm just gonna put this back. Never mind. That would have been too quiet. So this is the GD1 stream, this is what's called, it's being transformed into the stream coordinates, which is a very nerdy way of saying we rotated it until it was a straight line. So you can see the streams in the sky are like sort of all over the place. They're mostly vertical, they're kind of squiggly, all sorts of weird stuff. So when we want to work with them, when we want to do cool stuff with them, we just kind of rotate them until they're a straight line so we can actually look at them and compare them to other things. You can see in this stream, there's this sort of underdense region here where there aren't many stars. There's this weird spur going on here, and there's another underdense region here, and another underdense region here. These are all perturbations in the stream. These are things that weren't in the stream when it first formed and are now there. And we think these are caused by interactions with dark matter subhalos, which is a very fancy way of saying that there's stuff hit it, and we don't know what the stuff is. Dark matter, well, this is a brief review of dark matter. It's stuff that is in the universe, it's in our galaxy, it's around everything we know. We only know it's there because we can see the effects that its mass has on the things around it, like it bends light, it makes things move faster, all that sorts of weird stuff. So we know it's there because of the effects that it has, but we can't see it. It's dark. That's why we call it dark matter. We also think that every galaxy has a dark matter halo, which is the very large circle around it that has the dark matter. And there are these little smaller pieces of dark matter called subhalos that are inside this halo that are kind of flying around all willy-nilly, we think. And we hypothesize, there's a lot of hypothesizing in here, we're hoping this is right, that if one of them slams into a stellar stream or comes near it, its gravity or its physical size will knock some of the stars off of the stream, and you'll get this sort of perturbation, this gap here, or like something like a spur. The stars get distracted from their path by a dark matter halo. And you can tell the mass and the sort of trajectory of the halo based on what it did to the stream. This is very cool, because you can learn about what size halos you can get if you're looking at things like this. Here is one of my favorite plots in astronomy, which isn't even really astronomy. This is the different, what size dark matter subhalo corresponds to what theory of dark matter. Since we don't know what dark matter is, there are all sorts of theories for what it could be and what it actually is made up of. This plot has 1, 2, 3, 4, 5, 6, 7, 8-ish, maybe 9, I can't count, 8-ish theories on dark matter. We're pretty sure it's CDM, which is this like cold, straight gray line here. It's cold dark matter. But basically, different theories on dark matter predict different minimum subhalo masses. So like this orange line here, which is warm dark matter, predicts that because it's warm and it interacts more, you don't get as small of subhalos. So if we observe dark matter subhalos out here, we can cross warm dark matter off our list and say this thing probably is not what dark matter is because we can see this size of dark matter subhalo. This is why studying cosmology through stellar streams is important, because you can get the mass of subhalos by the perturbations in the stream, and then you can find some really small subhalos from looking at the perturbations. You can put them on this chart, and you can try to figure out what kinds of dark matter do and don't exist. That's the cool part. So what did I actually do? All of that was just background. I wanted you to actually be able to understand what I'm doing, so I had to talk a lot about, streams and dark matter and stuff. So I used data from the Dark Energy Survey, which is this very fancy observatory system that is on Cerro Tololo, which is on a mountain in Chile, much like the Rubin Observatory, which I'll talk about later. The Dark Energy Survey is a fantastic survey. It's been going for I want to say 8-ish, 10-ish years now, and its main goal was to look at dark energy, try to figure out what dark energy is. But I don't care about dark energy, so I'm instead using it for dark matter. So this is a very nice plot. This was created by Nora Ship, who I worked with over this quarter. This is a plot of a bunch of the streams that we know about. You can see they're being pointed to. Here's 300S. Here's, Palka. They have all sorts of fun names. This sort of white tank shape in the middle, this is the DES footprint. And astronomers have gotten very used to seeing this because it's a fun shape. And also, you get really good data in the middle, because DES was a very powerful telescope, and not as good data on the outsides. So we're hoping that LSST, which is this dashed line, will help us with that problem. So I want to point out 2 more things on this image, maybe 3. This one down here, these are the Magellanic Clouds that are the big dwarf galaxies around our Milky Way. They're blocked out because they're really bright, and so they would mess things up. Another thing that's blocked out, this is the Sagittarius stellar stream. You can see how much brighter this is compared to the other stellar streams. This is why it's a problem, because it's just so bright that it makes it hard to study anything else. And finally, I want to point out this little stream here. This is AAU, or Atlas Alika Uma, because they used to think it was 2 streams, Atlas and Alika Uma. Then they were like, hey, wait a second. Now we didn't know about perturbations. It actually was 1 stellar stream that got like a kink in it, because the dark matter subhalo got too close to it, and it sort of turned it into 2 things that look like 2 stellar streams. But it's still 1 thing, but it has 2 different named components. And if you can kind of extrapolate the tracks of where Sagittarius and AAU end up. You can see they'll intersect right there, which has made my life very difficult. So Sagittarius, stop that. So I studied this AAU stream in the DES footprint. Oh, yeah, I circled it. Well, that's nice that it would do that. It's right there. But you can also see that it sort of goes right up to the edge of the DES footprint. So the main theory of my project was that it looks like it goes right up to the edge, so I'm going to try to find an extension of it in a different data set. So first, here's the data that I used. This is a small section VES. This is what it looks like. It is just kind of a patch of sky. There are stars in it. There's some other stuff in it. These are like close bright stars or galaxies that are a little farther away. It's like whatever. This is just the data that I was working with before any sort of processing. So I need to introduce a concept called a color magnitude diagram. If you know what a Hertzsprung-Russell diagram is, you're really close. It's a very similar idea. On the x-axis, you have the color of the stars. On the y-axis, you have the magnitude. However, unlike the HR diagram, which plots like everything, every star you've ever found ever, this one, the idea is just to plot one population of stars and look at their color versus their magnitude. So this is their green minus their red color on the x-axis, and then their magnitude up here. You can see on this plot, there's basically a really bright section here, and there is some stuff here, but it's super duper faint, and you can't actually see it. And that was the problem, because the stream that I was looking for, I knew was like fairly over here in terms of color, and was also very faint. And so I needed to get rid of these stars. So I sort of cut them out, and now I am left with this sort of, I don't know what kind of shape this is. It's like if you took a triangle and then like broke the bottom half and angled it. This is what we kind of expect from one population of a cluster or a dwarf galaxy or something. Because these streams are from one source, we can use this to our advantage in finding them in the sky. Because they're only from one population of stars, you can just look for a thing that is one population of stars and say, that's the stream I'm looking for. So this kind of looks like one population of stars, which is helpful for me. I also need to talk about isochrones, which are basically a line on top of the color magnitude diagram for one population that tells you how old that population is. So all the stars along that line are the same age but different masses. So they're, farther along in their lifespan, even though they're the same age. Because they're bigger, they're sort of farther along, because the bigger stars are, the shorter it takes for them to die and explode and all that good stuff. So here's two examples of isochrones. It's called that. It's isochrone, literally same time. It is just a line of things that are the same age. What do you... Oh, there's a rat behind me. Nice. That's an isochrone. So I used a combination of a color magnitude diagram and an isochrone to try to plot the thing I was looking for. Now I'm going to introduce you to yet another kind of diagram, yet another kind of thing. This is called a Hess diagram. Not named after like the trucks, some astronomer named Hess. You basically take the color magnitude diagram for your region, and then you subtract out the background level of stars. So you calculate how many stars there are roughly in the background, and then you find some overdensity of stars in a region, and that's where your stream is. So this Indus stream has, a couple thousand stars in it. This one has fewer. And so you subtract out all the stars that aren't in the stream, and then you're left with this color magnitude diagram of just the stars in the stream that you're looking for. Then, if you draw an isochrone, like this, and you only plot the stars that are in that isochrone, you end up with something that actually could be considered a stream. So that's what Professor Shipp did here. You can see these two streams fairly clearly, even though they don't have many stars in them, just because they were selected via this matched filter selection function. You pick all the stars that match the filter, and then you select them. That's why it's called that. It's a pretty good name. So I use this method for the Alice-Aliku-Uma stream. Here's my Hess diagram. Here's the isochrone that I used for the Hess diagram. And there's the match filter. You can see pretty clearly, this is for sure a stellar stream. If it looks like a line, that's a stream. I don't want to hear about anything else that could look like a line on a plot. So this was good. This was good news. We already knew that it was here. This is in the DES footprint. And so this is just a confirmation that you can actually see it. So this is the Atlas part, and this is the Ulika-Uma part that's much fainter and is sort of askew from it. So this was the easy part, and the hard part was looking in the new data set. This is where DELV comes in. This is the Dark Energy Camera Local Volume Exploration Survey. They always have these fun logos. This one's like a shovel, because I guess you use a shovel to delve in the, I don't know, don't ask me. But you can see that it is, this white outline is of course the dark energy tank, or the footprint of it, and you can see that the DELV survey just kind of extends around it. And so we are trying to look in this region for our extension of our stellar stream, and so we're able to do that with DELV. So if we combine the two data sets together, you get something that looks like this. This is the side of the tank from DES, and this little triangle is from DELV. And I applied the same match filter to both, so you have this isochrone and this isochrone. There's some differences just because DELV is a little bit worse, and so it has higher error, which is always great when you're working with astronomy data. And you can see, here's the great stellar stream in DES, and I swear, you can actually see the extension of the stream in the DELV data. You can. There's a brighter sort of line that extends from the end of the AAU stream. You can see that the sort of end is right here. It extends there. Anyway, you can watch the tapes back. It's there, I swear. So you combine these two together, and then I was also asked to find, what was the distance they were at. So I made this cool GIF that, oh. Well, that's fun. Thanks. Anyway, speaking of Sagittarius, you can see that that's all up in this section. I don't know why this is doing that. I'll blame Megan's computer.
Yeah, it's probably like that.
Yeah, this is a really good GIF. If you were able to see it, it basically shows you that as the isochrone slides down to select a different part of stars, you're able to see the stellar stream more clearly. If you look like right here, it appears and then it disappears. So if you look here, you can also see that that part appears and then disappears with the DES stellar stream. That's the main part that I was looking at, because this goes away when this part goes away, which makes you think that it is in fact a part of that stellar stream. Yeah, this is a fun GIF that I made. Yeah, this is Sagittarius, and it's in the way. It's terrible. I tried to subtract it out, but I didn't do a very good job. Anyway, so that was the GIF that I made as sort of culmination of trying to find this extension of the stellar stream in this project. This project was, unlike most of the other Astro and Tap Talks that you see, only 1/4 long, so I didn't actually do very much in this project. This was just kind of the end of the project because I made a cool GIF, and if you squint really hard, you can say that the stream got extended. So that was my project, but looking ahead, I used DES and Decam data, but the Rubin Observatory is incredibly exciting for basically every branch of astronomy, but it is super cool for near-field cosmology as well, because even with just 1 year of LSST data, you can see fainter magnitudes than with 6 years of DES data. This is just because the LSST camera is better than the DES camera. So you can already see fainter magnitudes, and also, with 10 years of LSST data, which is, 10 years from now, we'll be able to get halo masses that are like, 10 times to up to 3 orders of magnitude more faint than what we could see before. So we're, calling back to before, if our main goal is to do cosmology with this, with LSST, we'll be able to see much fainter objects and much smaller halos, which is great. If you remember from earlier, this plot, if we're able to get, these dark matter halos that are down to like 10 to the 5, that means we can look at things that are like, we can cross interacting dark matter off our list, which would be very helpful, because there's some people right now who are very into interacting dark matter. And so this would be able to tell us if it exists or not. So this is very exciting. This will be super cool. We're excited about it. And if you're excited about it too, you can go to the Rubin First Look lecture that's happening on Monday. There's a QR code in Barbara's slide. She's more prepared than I was. yeah, so this is very exciting stuff that'll happen in the future. That was stuff I did in the past. Thank you for listening. Any questions? Yes. You in the hat. Yeah, that one.
You said stellar streams are like clusters that are going to stretch apart, right? Do they ever reconsolidate? Like, all that together?
So the question was, do stellar streams ever recombine into a spheroidal shape? And the answer is, we're pretty sure they can't. If you've heard about entropy, it basically says that as things, you can't really rewind processes that introduce more chaos into a system. So as this stellar stream gets, spread out into the sky, there's way more chaos, way more weird stuff that goes on. And so you can't really put it back the way it was. It also doesn't work like that gravitationally, because as it's orbiting, you're not going to be able to put it back together. It can meet itself again in like a circle if it gets really distorted, but it can't ever go back to a sphere. Yeah.
So this was one project as you try to figure out your PhD. What is this where you're headed, or was one of the other projects you worked on better at the future talk?
That's a good question. So the question was, this is one of the projects that I did. Basically, how did I feel about the other ones? It's something that I'll do in the future. I've done 3 projects so far. I'm going to do one over the summer, and then I'm going to pick what I want to do. So you'll be seeing more of me once I actually decide what I want to do and I work on a real project.
They'll be seeing more of you anyways.
That's true. But I did enjoy this project, and so I might end up working on this. Another thing that I might end up doing is what's called time domain astronomy, where I basically look at how interesting stars are changing on short time scales, which Ruben is great for. Yeah.
A couple of questions. Can you tell if the AAU stream is in front of the Sagittarius stream or behind it? And also, do you know where these streams came from? Do you know what the progenitors are?
Those are both great questions. The first one was, do I know if AAU is in front of or behind the Sagittarius stream? And the answer is yes. If I just go back to this GIF, that works really well. There we go. So in theory, up here, this is the distance modulus, which tells you how far away things are. And so as the GIF moves forward, the things are getting farther away. So you can kind of see both of them fading in brightness, but the Sagittarius stream sort of peaks in brightness here and then fades, whereas this one peaks in brightness there. So the Sagittarius stream is slightly behind AAU, at least right here, but it kind of is all over the place because it's a really huge spiral. And I've forgotten your other question. What was it?
Do you know what the progenitors of these streams are?
Yes. So very helpfully, these streams are almost never named after their progenitors. However, the Sagittarius stream is named after the Sagittarius dwarf spheroidal galaxy. That was really hard to say, which is where it came from. So that is the progenitor. That dwarf galaxy fell into the Milky Way and has formed the Sagittarius stream. Most of the other streams were just caused by little dwarf galaxies that didn't matter millions of years ago falling into the galaxy, or globular clusters. So for most of them, we don't really care about their progenitors. For Sagittarius, it's interesting just because it was such a big dwarf galaxy. Yeah. I can try. This one? Oh, this one. Yeah, so the question is, what are these 4 different things and how do they sort of come together? So these are the coverage of DELV in different bands of astronomy. So these are different wave bands, different wavelengths of light, because a lot of different things in astronomy happen at a lot of different wavelengths. So to get the most interesting stuff, you need to have a broad range of wavelengths. So this is the G band, which is roughly green invisible light, then the R band, which is roughly red invisible light, and then I and Z are both infrared light. So it is different wavelengths of light in order to see different kinds of things. and they have slightly different coverage just because of how the telescope was run. But when you take this camera basically takes a picture of one thing in 4 different bands, and you can get information in all of those bands. And
So, like, in the dark matter section, that means that that light is not being projected. It's just something blocking it, correct? How do you determine that?
so if you're talking about the perturbations in the stellar stream, it is basically, so dark matter does do interesting things with light, but what it's actually doing in that section is that it literally moves the stars out of the way, so they're not in the same place they were before. So the dark matter halo is sort of long gone. It's not in that area anymore. It's not blocking the light, and it instead has altered the course of the stars that are in the stream. Yeah.
So,
Yeah.
wouldn't that dark matter blob have a stellar stream being pulled behind it?
So the question was, wouldn't the dark matter subhalo that interacts with the stream have a stream behind it? And the answer is that not usually. Because they're going so fast, they don't have time to collect all the stars. They just kind of hit into the stream, and the stars that were there scatter, and they don't really follow the dark matter subhalo. It's more like bowling than it is like gravity.
All right, let's give Sam
Thanks, everyone.
a round of applause. Okay, let's give another round of applause to both of our speakers. Fantastic. So next month, we will have Astronomy on Tap on July 23rd. I have lined up a very special speaker for the month, but I'm not going to say his name because it would jinx it. He's very elusive, very hard to get a hold of. But it does maybe potentially have to do with Ruben, if he shows up, which he said he's going to. So, July 23rd, check our social media for Barbara to reveal the name of the speaker once I email him again. And we will see you all next month. Thank you.
Okay. So
Thank you.
This month's astronomy is that. There's so many stars. She'll be back next week. It's